So my name is MalcomVetter. I'm local from St. Louis, born and raised. Actually live outside in Raleigh right now. You guys know what that is? It's a pretty good college town. All right. Yes, I live out to 600 acres back in that. But anyway, so I've been doing IT for 15 years. Really corporate vendor, the builder. Gave up on politics and decided to shoot features of code for a while. Right now I'm some breaker down. Trying to get stuff really. I think that's where it's at. In fact, actually, Raph's talk just absolutely energizes me because defense is so far behind. Can't win, right? Just go to one back. So anyway, I spent way too much time in school. I've got a bunch of CDs, and it's not what like you guys have. My thing I like to tell people the best is I just create credit cards for point of sale systems that you can check out at, guarantee it. And it usually gets my non-technical friends' attention. They don't get the other stuff, but that usually So today, we're going to be talking about credit card tokenization attacks. So we'll first do a quick refresher on what truncation is versus tokenization. We'll get into some terms. Then we'll talk about these attacks at the end of time to go through all this list. So real quick though, a quick poll. How many of you guys consider yourselves corporate vendors? So I guess most of you probably raise your hand. How many of you are builders? Okay. How many of you are breakers? Okay, so just a handful of you. How many of you implemented credit card tokenization as your employer? Maybe one or two. How many don't even know if you have that? You've got credit cards to take them, just trying to insure. Okay, maybe not one. If you come across this is still pretty interesting. So first off, truncation versus tokenization. So credit card truncation is PCR parlance. The verbiage for basically taking that middle 6 digits out of the middle of your credit card, a truncated credit card number can be stored in some systems per PCI spec without being encrypted, that sort of thing. If you guys are familiar with this, the card numbers are not completely random. The first sort of digits actually tell you what kind of card type it is, who the issuer is, varies by country and card type. For example, Visa, MasterCard, gas cards, things like that. The rest of the middle is the actual account number, and then that last digit is actually a check digit, which is important to us because that actually breaks down the complexity of guessing. So if you've ever sat and wondered, okay, so these guys said I can store this truncated credit card number without any kind of encryption. 6 digits in the middle, that means 10 to the 6th power total guessing, right? Roughly about 1 million in the worst case. Or in the average case, half of the guess is just a guess with that after credit card numbers, right? It seems like, computation, that's Python, that's maybe a second to generate that. But it actually turns out to be worse than that. With the Moon algorithm, which I don't know if you guys are familiar with, you might have heard is the Montana rule. That basically says that last digit in that credit card number is actually a check digit, right? So it takes it down a whole order of magnitude. And we actually only have 10 to the 5th power. So 100,000 guesses, worst case 50,000 on average. It's very easy to brute force this. But this is for offline attacks, right? So obviously, that's not very useful outside of these areas. But we're going to play with this in just a little bit. So if you guys are familiar with PCI, I'm sure you guys probably all had touched that at one time, really. PCI DSS requirement 2.4 actually has a warning that we're going to basically be exploiting here. So be extra careful. Credit card tokenization is completely different. So in that case, we actually have a token, which is a surrogate number that represents that credit card. So we're not going to actually store that credit card, we're just going to create a surrogate for it. It's usually unique to the merchant. So if I steal a token from Amazon, I can't go take it to Target and check out. It's meaningless outside of the context of that merchant. And really big companies usually have multiple merchant accounts, so even if I hijack one particular online reseller for that company, I can't hijack another like that. Right? So tokenization benefits are off the bat. Obviously, it takes some of your commerce systems out of scope. I wouldn't see mostly talk to QSA about that, not give the details about it. But the idea is there's a nice height of segmentation, right? So we have all these credit cards that are tokenized over here. So all the stuff that credit cards are, I can lock it down, nice small perimeter, and just press through that one card knowledge. Typically, as a result of your commerce apps, your storefront will have orders, will have tokens, probably also has a truncated credit card number, so almost always does. And of course, you have to think of this as kind of like credit cards are now cookies, right? So your Commerce app can't touch credit cards, can't get cookies, because it does, and the tokenization is moved, and it all falls in scope. So it's the whole idea, we got to keep that idea in our head, that this Commerce app can't ever touch a real credit card number. Then the payment app, of course, has real credit card numbers, and has tokens, and has those matches, right? Some of these tokens can actually look like, these examples on the screen, so it could be a hash, it could be a substitution, it could be a database identifier, just incremental, it's really bad, don't do that. But it could be, you've seen it. It could be just an encrypted value of the key, or the credit card number. And so the question is it's encrypted or is it key, right? And it could just be a random identifier, so it could be a GUID, right? So for today, from our discussion scope, what we're going to talk about is an enterprise target. We're talking about self-hosted tokenization, right? It's kind of DIY. You're doing it yourself. You're big enough to maybe handle out these. We're not really talking about payment gateway. So if you're using like CyberSource or one of the payment clearinghouses, we're not talking about attacking them specifically. But the things we're going to talk about could potentially be used against them. So this is really aimed at an enterprise. Also, keep in mind, we're not talking about breaking crypto. There's no magic crypto fairy dust in this. We're just going to look at the scenes where these systems glue together. We're going to kind of feel them apart. So, first up, malicious insiders. We're going to define a malicious insider as somebody that is probably IT support personnel, right? So this is your system network, DBA, could be a developer. That person that knows about your Commerce app. They either deployed it, they supported it, they've got access to code, they're building the code, whatever. They know this stuff. So they know inside that Commerce app, they've got the billing info, so the customer's name, address, which is important because once you want to commit fraud, you have to have that, not just the number, right? So credit card number by itself is useless without having all the relevant bits to go with it. That will also have probably truncated credit cards because that's the whole point of truncation is you can store it anywhere, right? And they'll have access to tokens because the tokens are in the Commerce app. And then, of course, they're going to have knowledge of that tokenization architecture. So they're going to know the web service that you're calling or the APIs. They're going to know the URLs for that stuff. They're going to have maybe access to logs. They're going to see example requests maybe. They're going to see all this. They're going to know this. This is the person we're talking about. And a large scale retailer, you're potentially this list is maybe hundreds of people actually. Right? So best case scenario. So if you are an enterprise that does tokenization like this, the best case scenario for you is that malicious insiders, the level of effort is equivalent to just enumerating credit card numbers based on the truncation law. So that example we showed a minute ago, 10 to the power, right? A whole bunch of guesses. 50,000 on average. So in this case, we would be talking about an online validation. So you can't just guess this thing. I actually have to send a credit card through end to end from the Commerce app to the payment server, that bank, and back to say, see this valid, right? Basically try to run an authorization on an actual transaction. So in this scenario, of course, you're going to have fraud detection, you're going to have throttling, and this stuff is pretty much the same day. This is a great spot to be. So if you guys want tokenization, and this is where you're at, this is the worst case your malicious insider can do, pat yourself in the back, you're probably pretty safe. But the worst case scenario, and mind you, these are all, everything I'm going to talk about today, these are real things I've seen with actual clients. And some of these exist after today and not fixable. So, tokenization role is actually internet-facing. It's on the internet because it has to be, because your customer, the online customer, is going to be typing in the credit card directly to that tokenization service. It's going to go from their browser with that, so it has to be on the internet, right? The Commerce application is going to perform authentication, right? So if I'm John Smith, I log into my poolstore.com, I do my transaction, I got my shopping cart, I got my profile, and all that good stuff. I've authenticated there, I've got sessions, I've got all the good stuff that awesome says to have my web app, my developers are trained in the top 10, we're good, right? Except for the problem is we hand off to that transaction against that payment service. Almost every single time, the payment service is going to actually authenticate the request. And there's a reason for this. Your payment service is going to be in a different EMZ, right? You've got this PCI, secure, whatever you want to call it, domain. And inside that place, it's usually could be in a different data center, might be hosted someplace physically different. But it's physically separated and it's logically separated. So it's going to probably have a different DNS domain name, which is going to come into play when we're talking about session cookies, because session cookies are tied to the domain, right? So it's hard to get that stuff across. And of course, since they're separate, we can't share session state. And I'll show you some examples of why this is important in just a second. And the other thing to keep in mind, so since this is on this other side, and it's authentication of the payment servers. It's almost impossible to do any kind of request logic. So I can handle anything. I've got clients where we hammered 100,000 requests inside of a couple minutes, right? The environment was really, really large scale. It was designed to handle it, and it was really handled without even notice, right? They didn't even know that we were hammering. So this is very, very typical. And so I won't use the word threat intel, except just now. But I will use the word zero day. This is kind of like a design flaw zero day, right? And that's it for the policy. So anyway, so worst case example, let's look at this. Got a customer, let's say that we're going to store.example.com. They're up there, the browser's getting ready, they've got this shopping cart built with the products they're about to buy from you. And what they do is they actually get ready to post that credit card. So they get to that checkout page. There's a variety of ways some of the services do this. In old school days, it was an HTML form that the action for the form actually said, here, go over to this other web service, post over there, and then get it and do this clunky thing. In fact, if you guys remember like IE 5-ish, 6-ish days, where every time you took a link, IE would do that little clicking sound. This would be example by you drew like 3 of them because they would come back and JavaScript would redirect you back to the main app. And that's this really clunky kind of duct tape kind of way to keep that flow going, so you seem like you never left your actual storefront, which you did. So that's the old school way of doing it. I still see that from time to time, but we've got JSON, REST services now, right? So this is the new school way of doing it, and I saw an example. This is based on an example from an actual store that I tested maybe 3 or 4 months ago. So this is pretty fresh. So post request goes to payment.example.com. Notice that's a different domain name, right? So obviously cookies are different, right? So if store.example.com just sets a cookie down for the session and doesn't explicitly say, hey, this is good for everything on example.com, the cookie will be restricted to store.example.com. So when your browser makes that post over to payment.example.com, that cookie doesn't go with it, right? That cookie says, no, you can't have that cookie. This is for this other thing. So here you go. You got a request, no cookies in the header. This is very common. If you go ahead and set that cookie to say, hey, we're going to restrict this to all of example.com, the entire company's root domain, great. It's still come across, so it's not going to mean anything because there's no session state on this other server. Remember that this is separate. They're not sharing session state data, because if they share session state data, that means that they're probably too touchy-feely, and they've got 2 credit card cookies, right? So that app server would therefore be in credit card scope in, and then you have all of these separate regulations applying to it. So that's not going to happen. And if I'm a bad guy, and these 2 guys are separate like this, even if the cookies do come across, I can just strip them out, right? I can just send a request all day long like this. So here we go. Our typical response is going to be something like that. You're going to have 200 OK status. Here's your token. Great. So what did we learn? I send a credit card number to this thing. It gives me a token. Sounds pretty cool, right? Credit card, here's a token. Here's a new credit card, here's a new token. There's no access denied message. It doesn't have a credit card. I already have a session cookie. There is here's a primary account number and here's my response. So think about what malicious insider can do with this. So back to that whole truncation, we can calculate 10 to the 5th power, roughly 50,000 guesses on average, right? We can calculate all those possible paths, those primary account numbers. Get them all set up ahead of time. Write a little Python script about 10 lines long, and just get ready for each one of them and send a request anonymously at this payment service, right? And just collect all those tokens. Remember, I'm a bad guy. I've got the tokens, I've got the truncated cards, right? So if I've got the tokens in my database and I can see the tokens, I'm just going to fire across, and eventually, if I get a response token that matches the token in my database, I get your credit card number, right? And I'm a malicious insider. I hammer on this thing, I extract all the credit cards out, and I go sell them because you don't pay me enough, and I'm going to find somebody right that posts this on a inside of it, right? So this is pretty simple, but this I've seen countless times. So here, why is routing on the payment server actually difficult? So we kind of hit on this a little bit. So unique cookies, there are no unique cookies that come across. Even if they were, like I said a minute ago, attackers could just throw them away. You can say, well, I'll just block the IP address. Okay, great. You have any customers that are behind that. You can't do that because then you're going to break legitimate business and you don't want to stop revenue flow, right? So you'll never get that flat legally, right? What about what the bad guys smart enough to get a cloud or a botnet that does the equivalent of like a Bitcoin data mining, right? You just go hammer at the service from different points. They all have different potential solution that we recommend on this particular example is, if you're familiar with federated identity, this is not new, this is not monumental, but the solution is, hey, let's do some kind of federated authentication handoff. So when I send that request over, validate that actually came through. And there are actually some clearing houses that I've seen that do credit card tokenization as a service to their merchants that do something similar. So this is just the idea that we're going to assign this set of parameters or whatever. This really they come from, where we say. And by the way, if you're going to do this, don't implement this in JavaScript. Right? JavaScript can be viewed by your attacker, right? I've seen things like that too. So again, this is all RESTful service stuff, right? So it probably means there's some JavaScript on that storefront, on that checkout page, that it's in the user's browser. It's right there. It's going to go grab this data, grab the credit card field, get that value, go encrypt it, go sign whatever it needs to do, and then go fire it off. Well, if I'm the bad guy, I can do it in JavaScript. I just read it, I go emulate it, I go port it to Python, and I go hammer at it, and I'm done. I'm in. So that's that. So side channel attacks. Side channel attacks are absolutely my favorite variety of attacks because there's something you can just never really anticipate, and it's really, really hard to defend against. By definition, if you guys aren't familiar, this is between an unintended channel and information flow. So we're going to look for a 1 or a 0 and a bunch of noise. And if you guys want some extra credit or if you're just absolutely, sadistic, you can go dig up a copy or an EE book on Shannon's law or Shannon's theory of information. That's all you're really doing is you're just applying Shannon's law. So there's three things we're going to look at. We're going to look at some timing attacks, something I call a micro-profile attack, and then some helpful headers. So timing attacks. These are actually extremely difficult to prevent, and it's absolutely, I have on yourself considered by developers, but in reality, we send these developers to school, we tell them to be as efficient as possible, right? And you'll see here in a second, we actually ingrain in their heads to create this vulnerability for us, okay? So the trick that we're going to export here is we're going to submit previously unused credit card numbers, PANs, and then we're going to record the response times, okay? They're going to be batch. And then we'll send the same batch for the second time, and then we're going to look at the response time the second time around, and then just kind of compare the deltas and see, is there anything predictable about it? I've tested some where you send a whole batch through, and the second time around, it comes back really, really fast. So maybe 300 milliseconds the first time, 100 milliseconds the second time. Or the reverse, we're actually seeing the reverse is true. So, again, this is inspiration for this kind of attack. It's not from a malicious insider. Somebody's got access to a truncated PAN, right? Where they make it to a customer's account. So if I'm a bad guy and I can steal your customer's micro-login, their account passwords, right, or steal session cookies, right? I get in there, I log into the app, and I've got I can see the Visa, these last 4 digits, this is the expiration date, you're filling in, blah, blah, blah. Now, what can I do with this stuff? This is a slightly sanitized version of results that are very, very similar to what we've actually tested in the past. So you can see here, we stand around a bunch of random credit card numbers. You can see the average response time is around 300 milliseconds or so. And then at the end, we've got one that's about 100 milliseconds because it's one that the payment server has actually seen before. And so what does it tell us? Yeah, that's the one we're looking for. So, pseudocode. You guys, everybody knows pseudocode, right? So this is kind of what this particular app was doing in that situation. It was taking that credit card number, generating a SHA-256 hash of it. It was basically saying, hey, select all the credit card records in the credit card table where that hash matches. And if there aren't any, go ahead and insert it. But if there are, let's just go ahead and return that hash. We've already found it, right? So if you think about it, if it's a brand new token, you're going to go out and get that database twice. And what do we know from basic computing theory, right? I/O is slow. I/O locally is slow. I/O to another server is even slower. I/O across the network, slow, right? So if you're going out and getting that database, that's where that extra latency is coming from. So in this case, response times, where we got server responses back around 300 milliseconds, that tells us, hey, man, this is not the customer's credit card. This is obviously a new credit card that this thing's never seen. Make sense? So, timing attack solution. This is where we're going to go ahead and unlearn everything we teach developers. We're going to go there and say, hey, you know what? So there's obviously 2 logical paths. There's a logical path in our code that says this is the right credit card, and there's a logical path that says this is a credit card we've already seen before. What we need to do is we need to make those two paths roughly indeterminably the same, right? We need to not be able to tell that one is faster than the other. So we need to actually intentionally introduce inefficiencies on a fast go path. That one that only hits the database twice, you got to fix that based on that. So developers usually just want to send a recommendation. They say, but this might also be that upside, right? That's not what we do. So here's things we recommend. So you can say, hey, just do one sort of random arithmetic. That tends to be pretty predictable, but you can do it in ways that make it less predictable. You can go ahead and just hit that database a second time, just go select it again. That's not really efficient. DBAs won't like you for that. Right? Hit the database a second time when it's not necessary. But that, if there's a realistic factor that's delaying that response, hitting the database a second time will actually make that more equal. So environmentally, so in today's, the database is running slower. So if you deliberately sleep an exact extra 200 milliseconds on the day your database is chugging along and just eating a brick, that's the day that the bad guy still has an advantage, right? So hitting the database a second time actually does have some advantages. So let's talk about another side channel called, we just like to refer to it as high-profile attacks. So again, this is a scenario where an attacker has stolen either session cookies or credentials. So they've done a phishing campaign, they've successfully gotten your customers to log into the website, and they've grabbed those credits, right? So now they go out and hit your site as that user. The first thing they do is they say, okay, let's go look at all that truncated primary account numbers that are sitting out there on the My Profile page. And the developers usually at this point say, yeah, we deal with it. That's just truncated payments, right? It's not even a PCI scope, right? It's just tokens. Okay, but we'll see here, this is something that we can literally do on tons of sites. There are very, very big ones that I shop at regularly that I still shop at, because we all still shop at that actually have this vulnerability, so we're going to hit here. So the trick that we're going to do is we're actually going to have, as an attacker, we're going to submit a possible pan just like before, so we're going to pre-calculate these potential matches for that truncated pan using the same billing information, because it's going to be showing up right there. We log in, how many people have seen that, right? You log in, go look at my credit cards, and this one's expired, so you can go add a new one. And there's the old one that's got the masked number, or maybe just the last four, and this is the Visa. So the fact that it's the Visa already, maybe it's not just 10 to the 5th power in this case, because I don't have just 6 digits. I might have to pre-guess those first four too, but those first 4 digits are within a formula, right? Visa only has so many digits, MasterCard, Amex, whatever. So what we're going to do is we're going to generate those guys, and then what we're going to do is just we're going to go try to add a new card to our profile. Okay, simple enough, adding a new card. They use the same billing address, so that's a match. We're going to try to guess that same truncated pan. We're going to try to guess the missing digits. And then we're going to look at the number of credit cards that were on my payment methods in that particular profile page. And if the number of credit cards is the same, we won. Right? Because we just added the credit cards. What developers do? Man, you've already added that card. I'm not going to add it the second time. It's already there. Right? That's how developers think. If you see the number of credit cards in your profile increase by 1, well, dang, we missed. So for bonus points, make your script delete the one that you just added, right? So because I've actually seen some apps show once you get to 100 credit cards on my profile page, maybe at that point a developer will pay attention to the fact that you're hammering away your app or sysadmin or whatever. But otherwise, generally they don't pay attention to this stuff. Your SOC isn't notified. So that's all we're going to do. We're just going to hammer at it, give it a new card, and see if the account goes up by 1. If it doesn't, we got a match, we won. So what we're really doing here is we're basically trying to elicit a Boolean true-false response, right? So if the card is the same, true, that's match, credit card. So solutions. What we tend to recommend is that on developers that have done this, we say, hey, just add new credit card record anyway. It doesn't matter if the system owner behind the scenes is using the same exact value, but just pretend, go along with it, so you don't give that true-false logic back to an attacker, right? Add new credit card record even if it's perfect match. So, application servers are typically going to look at the token value. If we just generate a new token or it's the same token, create a database ID to reference it, so I've got 2 copies of the same token. Again, we're introducing inefficiency. Developers don't like that, but in this case, that obfuscates and hides what we just did, right? It doesn't give us signal back to the attacker. Helpful headers. I've actually seen this. So how many people have RESTful service geeks working for their company? You got some developers that just like they're into it, you know, and they want to have like apply to the nth level. It's not just we're going to do get and post, but they get the posts and deletes, and they got all, you know, they're just into it. And every single response code has to be used. It has to be used according to what the latest Twitter feeds say and how it needs to be used, right? I would love it when I get a test like this, because those guys are the ones that are going to give me an extra signal, right? For example, what happens if I send a token or a credit card over and say, hey, give me a token, and I get a 201 created versus a 200 okay? What does that tell me, right? This guy, if you read the logs, when you add a new record, you send 201, obviously. When you have an existing record, dummy, it's 200 okay, already got it, right? So now I just, you know, all I can do is hammer this thing until I get 201, right? 201, or excuse me, until I get 200. 201, ignore it. That's a brand new record that just created. That's obviously not the token. It's obviously not the customer credit card. Let's keep hammering on until I get 200. Cool. All right. So now let's talk about some careless customization software bugs. Okay. I've seen these as well. These are definitely in the oops category. We've had examples where customers' browsers have accidentally sent primary account numbers back to the commerce search, back to the main store. Remember, these are cookies. This violates everything. Your QSA finds out, your rock's not going to get signed, and your company is going to have all, you know, this CIO is going to be wondering why your project is failing, right? So this is kind of another list. For example, voucher bugs, we've seen that. Big complicated code files where we've got little widgets that you guys can call that the developers don't understand how they work in certain edge case scenarios. Bad things happen. Oops, I accidentally sent the credit card back to the app server, you know, mistakenly. Edge cases that your QA team doesn't test. So how many people have web developers that use Agile? Anybody? Yeah. You know, these guys like to throw new features out, and you got some QA team that's doing regression testing, right? And how many times have QA teams missed some edge case because their regression tests don't include it, right? This is the kind of stuff we're talking about. And this will be something that, well, we implemented a feature like last year. How come it's not a problem? You know, well, because you guys didn't test it. So here's one of my favorites is ASP.NET Web Forms. I'm a C# developer. One way or the other, I fell in love with it to a degree. I'll have to do that. I'll go to my 12-step program later. But it's, you know, if you guys remember the original Web Forms days, when Microsoft was trying to be Ajax-ish, they did things like increase these controls and these partial page updates. So, you know, so it's not, so you're not reloading the whole thing. It feels, you know, fresh and new and more high-tech than Web 2.0 back when it was brand spanking new. So my favorite ones are the form validators. So you'll see, because I mean, this is a really complicated thing, right? I have this checkout page, it's got all the billing information, it's got what I'm shipping into, the check the box, the matches, all that jazz. And it's got credit card numbers, we're going to have one form, you know, simple, streamlined user experience, right? And unfortunately, there's some stupid address validator that runs amok. And it accidentally, when it validates the address, it says everything is in the form. So every form field goes back to the server, right? Well, so your developers have these nice Visio spreadsheets and architects that sign off on them, and the USAs look at them, those and stand up approval, and it's been, you know, not deployed for 3 years, you know, PCI compliant all the time, but you don't realize when it comes down to it when you actually test your app, that your form is probably sending the actual unencrypted full credit card number back to the web server. Your server-side code is just ignoring it, it's not looking at it, but it's still there, right? See this all the time. So the example, sanitize request, where you get, you know, script engine one, update CC number, so this is obviously some little thing that's just running some check, and boom, there it was, the card number. In fact, sometimes you ever see the card number and the card number validation rate type in twice, it will come across. There you go, patch yourself on that. Right, including the CDD number, right? That's seen that too. So, in this case, the solution's simple. If you guys are thinking you have development background and you do anything with the ASP.NET world, you've probably seen the t-shirt that says friends, don't let friends, you post back, and you switch it and you see, right, this is there's Microsoft solution, it's not that framework anymore, be careful about those things. Some more JavaScript bugs. So I've actually seen, this is another one, there was a web app that we were testing that it wanted to repopulate that card type. We're just going to have that user type those first 4 to 6 digits, and that determines what's called the BIN or the bank ID number. And what we're going to do is we're going to send this briefcase off. Well, this their shop had a little problem with the way their JavaScript code ran. And every key press, it would send whatever was in the credit card, right? So it was first, if this is a classic test visa 4 and 15 ones after, first it was 4, then it was 4-1, then it was 4-1-1, then it was 4-1-1-1, and guess what time? So they got to 15 characters. Now, what do we know about the balloon check? Balloon check, if I got the first 15, I can copy it to 16th one. It's like, what, 0.00003 microseconds, right, to actually do that. So, yeah, that's a big bad bug. And on top of that, technically not be set for it. Another example I've seen, so inside the HTML, you have your nice form tag. And so these developers that love the JavaScript frameworks, we don't set the action on those form tags anymore. You know, we're above that. We're going to programmatically do it in JavaScript, right? As the page builds in your browser, we're going to have all these cool JavaScript libraries that we found on Twitter yesterday. And we're going to go ahead and use those to change the action and send it back wherever it needs to go. And then guess what? One of them's going to hang because there's going to be some weird thing. You're going to have some customer that's running IE6 or something stupid, and it's that JavaScript framework's not going to fire correctly. Or there's going to be some kind of weird latency issue because your JavaScript is actually hosted on some cloud server, right? And it's just not going to load, so it's not going to properly override that form action. And so when that user types in their stuff, it looks all pretty, it looks the same. It submits their order, it posts back, straight back to your app server, right? And if it spooks and the order is broken and whatever, maybe the user will reload the browser, maybe by that point, whatever connectivity issue is resolved and pulls down JavaScript and it updates. Or maybe that bug goes away on the second load or whatever, or maybe the user just gets frustrated and doesn't complete the order, which would be a bug maybe eventually get around fixing. But in the meantime, you send a credit card can straight back to the app server, which means again, gratuities up to the app server, technically these have the client. And you'll see here in a second, there's other things you can do to the app server at that point. So we talked about Agile setting. How many people love the term DevOps? See, I have my own buzzwords. I'll say threat intel, third time. I'm not talking about that. DevOps, here we go. So DevOps, centralization, and beauty. So, in the world of DevOps, we have these configuration management or build engineer guys that are kind of pseudo developers and pseudo admins, right? Behind the people spaces. They're going to help us out by building our stuff. We're going to have continuous integration. We're going to ship new features like hourly or minutely, and we're going to get that out there. Great. What do we know about JavaScript? JavaScript does not actually need to be compiled by the build server, right? If you've got a Java app, it's got to build Java stuff. C#'s got to build C# stuff. If PHP is just thrown out there and any other scripting languages, the code just shipping out there. But JavaScript stuff, same deal. It's just going to get pushed out the server. It's going to live on the file system in a certain spot. So there's not going to be any build events. There's not going to be any, hey, you checked in crappy code and built, and there's our code review tool that we bought that checks for security flaws. Isn't going to just find this and throw a big fit about this, right? That's just going to be transparent. If the DevOps guy decides to hop on the admin box in support mode and he's got admin rights out there, and he goes out there and he just tweaks that JavaScript, right? What if he decides that form, rather than post it out there to payment.example.com, he's going to post it out to his evil.com, right? And his malicious website is just going to grab that same deal and it's going to post that same value straight on back on over to the original original payment.com and just back the old there's the IE6 and click, right? You guys remember that? So in this case, your DevOps guy can slip in, you can make changes on the box. You're probably not going to have any custom out of off-the-shelf SIM tool or intrusion prevention tool or anything else is going to be aware of this. This is very unique to your app. How many of you guys are actually monitoring this? So what if they do this? They can steal credit card straight off your app and they can override the JavaScript call right back. And just do it every once a day for a couple hours during a peak business time and just do credit cards that way from it. Branch scraping. So branch scraping obviously is a big deal with point of sale systems, right? So I have to put a big note on here. You can scrape RAM on web servers as well. It's not just unique to point of sale. It's anywhere there's something unique of value that would live temporarily unencrypted in plain text memory, right? So even if your website is HTTPS, even if you have tokenization in place, you have one of these aforementioned bugs we just said where either DevOps guys maliciously sending it in, and actually this is not the way they do it. A allow that credit card number to come post back to the app server accidentally. Because if they do, they can just sit there and look at the logs, or they can scrape the RAM themselves, right? Using tools, debugging tools that are probably whitelisted. I was on an engagement recently where System Suite was completely whitelisted on a point of sale environment. That was awesome. Thank you guys. I dumped credit cards straight out of my point of sale. Your good guys that are malicious insiders should do the same thing. So just because you've heard RAM scraping, anything out on point of sale systems, they can't steal my credit card, doesn't mean that's true. Well, the other fun thing about this, on this one particular point of sale system that I've tested multiple times, if you put a credit card number into that, it lives in RAM for hours. Think about that for a second. You swipe that card, that point of sale system, it lives in RAM for hours. Any of those Java and .NET applications use garbage collection, so that memory is just going to be allocated until your garbage collection decides, hey, you know what, let's free this memory for something else. Your web apps do the same thing, garbage collection. So just because you have an accident like that, or you have a malicious insider, they don't have to be sitting there in real time, grabbing that minutes of work, running it, hourly, doing a memory dump for diagnostic purposes, every hour, cron jobs, stuff like that. This is the scenario. All right, so that's it. We went through a lot of stuff pretty fast. Do you guys have any questions? Yeah. The only countermeasure against RAM scraping is don't put data in there in the first place. Right? Any data you don't want in there in the first place. So in the point of sale environment, that means don't have any unencrypted credit card numbers ever enter in. So in a traditional brick and mortar place, when that card is swiped through the payment entry device, it needs to be encrypted right there. When it's passed off down that serial cable or USB cable or whatever it is, and it gets in the memory, that data is already encrypted. So that traditional operating system that's running there, you can't use a really like tool anything. That's the idea, to make it as minimal footprint as possible. And in the web app space, there is no solution to that. If the card number comes into the web app, it doesn't matter if it comes in over HTTPS, encrypted in transit, right? Your web app, your web server is going to associate that value with plain text, and it'll use something with plain text. So just don't do it. Anything else? I hope this is not more depressing after you just have a really hard time as vendors in the first place. I totally sympathize with you. That's why I'm on this side of the fence now. I just quit and gave up. But the reality is we have a huge challenge in front of us. Testing like this is important. So if you guys have apps that you're not sure how strongly built and implemented they are, by all means, hit us up. We love breaking and hope you guys